Alright, so good day. My name is Loise Rebuelta and I am your today's lecturer. So there will be two topics to be discussed, but in every two topics there will be three additional methods that will be taught in every topic. So first, this is actually the application of integration and areas and volumes. So for a topic of under areas, there are under the curve, between two curves, and polar areas. For the application of integration in volumes, there's also three methods. That would be now this, your shell, and your washer method. And so, please take a seat, get your pen and paper so you could take down notes, and please enjoy and watch my masterclass video number 2. All right, so let's get right to it.
All right. So good day. This is Loise Rebuelta, and I'm a regular lecturer for today, and this is master video number two. Master classes video rather. Master classes video number two, and our topic for this master class video is the application of integration. So actually, we have two specific application of integration, and that is with area and also with volume. So first is the integration application of integration in area and volume. So the topics in areas, that would be areas under the curve, areas between two curves, and polar coordinates. So let's get right to it. So the first topic would be the under the curve. So for under the curve, there's two strips that you need to be memorized or rather familiarized with. So there's a vertical and a horizontal strip. So first, I will explain the vertical strip. For vertical strip, we have a curve here. And under the curve, there's a limit of A and B. The limits of A and B, and you can actually put here this is what you call a vertical strip. And this vertical strip has the distance of from with connect with parallel to the y-axis and its length, and width is from the origin here or the y-axis here from this strip, and the thickness of this strip would be your dx here. So again, this is your length and your width, and this is your dx, and this is your horizontal vertical strip rather. So and actually this is the area of concern. And so for the derivation of its formula, so that would be now the differential area is equals to y dx, because we put out the strip, the vertical strip, and this would be now its very example is that in from top to bottom, that would be now its y, and the thickness of the strip would be that it's dx. So if we can derive that, we integrate the differential area is equals to integral of y dx with limits from a to b, and that would be now the area is equals to the integral of y dx from limits of a to b. And for the horizontal strip, so this could be now I have here a curve, and the curve here has limits from a to b, and for the word or the word that says horizontal, so it's horizontally, so it's parallel now with the y-axis. So from the y-axis, from the y, or rather from the x-axis, parallel from the x-axis. So from the y-axis here, from point here to point from the tip or the intersection here would be your x, and from the distance from the strip to the x-axis, that would be now your y, and the thickness of its vertical or horizontal strip rather, that would be now your dy. So if we take out the horizontal strip, that would be now here the from point here to point there, that would be now your x, and this is now the thickness of its horizontal strip, that would be now your dy. And if for derivation of its formula, It's the same as the vertical strip, that it has the differential area of x is equals to dy, because it has your x and this has your dy. So there's now if you integrate the differential of area and y dy, you get now the a, or area, is equals to the integral of x dy with limits from a to b. So I don't want you to memorize the formula, but rather understand, because actually, if you can derive, if you know the vertical, you actually know the horizontal. If you know the horizontal, you know the vertical strip. So let's go right to it. For example number 1. For example number 1, find the area under the curve y is equals to 5x plus 5 with the limits from x is equals to 0 and to x is equals to 7. If you can plot if you don't know how the plotting of 5x plus 5, you can actually do the tabular method, and that would be now if you plot here x and y, and if the x is equals to 0 here, as you can see here, if the x is equals to 0, 5 times 0 is 0, and your y would be now is 5. And if the x is 1 here, 5 times 1 would be 1 plus 5, that would be now your 10. So as you can see, I've already set the grid or the Cartesian plane. Now I'm gonna connect its plotting rather. So I put here, this is now your 0 here, and this is the 0, 0 origin. So from x is 0 and 5, x is 0 and y is 5, it would start here. So if now your x is 1 and your y is 10, so it would be now here. And remember, you have the limits from 0 to 7. So if you connect here the line, and you label the line, that is y is equals to 5x plus 5 here. So you could now, your limits is only until 7. So this would be now your area of concern. So in areas or application of integration, the most important thing is how you label everything. So everything should be labeled. So you can now put here x and y, or x or y, and actually you can pinpoint anything anywhere you want that you would like to put your strip. So what we would like to do now is the horizontal strip, or rather the vertical strip. So now for the vertical strip, I've already put here the strip here. So from the bottom, this would be now the thickness, and that would be your dx. And from the top here, this would be now your, because it's parallel with y, so this is your y. And you could now, from the origin here, from y, and it's now parallel with x, so that would be now your x. And this is your area of concern. So we could now plot, we take out the horizontal strip, or rather the vertical strip here. So we label it as your y, and this would be now your thickness, or rather your dx. So as earlier, the formula for vertical is that the differential area of y is equal times dx, and you integrate this, it would be now area is equals to integral of y dx with limits from 0 to 7 here, or here, that is your 0 to 7. So if you now straightly, so that would be now x, and you now substitute y, that is 5x plus 5. So the integral of 0 raised to 7, or rather the limits from 7. So this is now 5x plus 5 dx. And so now that would be now area, and we now integrate this. So that would be 5x squared over 2 plus 5x with limits from 0 to 7. So the 0 is automatically, so you can cross out that. So that would be now 5 is equals to 7 multiplied by 7 raised to 2 over 2. And your answer would be, if you now calculate that with your calculator. Where's my calculator? Just a second. I'm trying to find, here's my calculator. So that would be now 5 divided by 5 multiplied by 7 raised to 2 over 2, and that would be now your answer. And or rather, don't forget actually the 5 here, plus 5 multiplied by 7 also. So let me do it again. So plus 5 multiplied by 7, close open parenthesis 7, and the answer is 315 over 2 squared units. Actually, you can do this at this point here. You can actually input that in your calculator. You have this, your integral sign here, but our professor really want us to do it manually, so we're doing manually. So actually you can check your answer if it's correct, and sometimes you maybe get it wrong. It's because on how you derive this formula from your integration. So you don't blame your calculator for giving you wrong answers. And that's for now, that's for the vertical. So let's, for number 2, or the problem number 2, and specifically that's for your horizontal strip. I would label this as horizontal strip. And for your horizontal strip, find the area under the curve x is equals to y squared with limits from y equals to 0 to y equals to 4. So this would be x squared, y squared, and this would be now a parabola. So if you don't know how to plot a parabola, you should do the tabular method. If I put 0 here, you erase 0 by 2, that would be 0. If I put 1 here, you erase 1 to squared, that would also be 1. If I put 2 here, your answer would be, your y would be 4, because 2 raised to 2 is equals to 4. I'll be only focusing on the one side here. So this is your 0, and your x is 1 and 1. So I think this would be the point. And your x would be 2. I would put 2 here, and I'll just put a 4 here. So this would be now your 4. And actually now your parabola is taking shape as like this. This would be now your parabola. So in horizontal strip, it would be now parallel with your y-axis, rather with your x-axis here. So it has limits from 0 to 4. So for the sake of, I have a small illustration, I'll just put your label is as your 4, and this becomes your 0, and this would be only your limit of 4. And don't forget always to label your lines, and this would be now the line, or rather the parabola would be x is equals to y squared. So now for horizontal method, or rather horizontal strip, I would label this now as your, I can actually, then you can pinpoint anything or anywhere you want. So you could create here your strip, and and this is now would be your strip. And from the origin here, from the parallel dot to y-axis or y-axis, that would be now your x, because you're parallel with your x-axis. And from point here, from down to down with parallel to y-axis, and that would be now your y. And the thickness of this strip, that's what we call be your dy. As you recall, in our formula here, that would be the differential area of y dy. X rather, differential area of x dy. So, you can now shade your area of concern. Then now, if you can plot out, now your strip. You could put it here. This would be, the thickness is your dx, or rather your dy, and the length here would be now your x. And now for the formula or derivation of its formula, that would be now the differential area is equals to x dy. So to substitute the differential here, you could integrate that, and that would be now your a is equals to differential of x dy, or rather a is equals to integral of x dy with limits from a to b. And as earlier, your limits is from 0 to 4, or rather here from 0 to 4. So you could now put it as the integral of x, and your x would now be your y squared. Don't forget that if you have your dy here, your variables also would be y. If your variables would be x, your variables would, if your dy, or rather is y, you put y. If your dx, or using dx, your variable should be x. So now that would be your x. Substitute your x is y squared dy with limits from 0 to 4. A is equals to, you could actually straight integrate this, is y cubed over 3 with limits from 0 to 4. Could actually cross out 0 because it will become 0. So that would be now 4 cubed over 3. And if you get your calculator, 4 divided by 3 raised to 3, your answer would be 64 over 3 squared units. I will teach you a shortcut here. As you can see here, you could actually input this in your calculator. So go to first your shift, or rather go to your mode, or rather shift mode. You put always rad, you put 4 radians. Then you go for the integral sign here with has limits. You could now input alpha x squared. Actually, would, even if it's y, you use x, because the system of the calculator always use dx. So you just substitute x as your, or substitute y as your x. So that would be now x squared with limits from 0 to 4. And the answer would be 64 over 3. And 64 over 3 is our answer. And this is now a correct answer. So this is for application of integration in area under the curve. So for the next video, or for the next topic, would be areas between two curves. So I'm gonna get a new piece of paper for the integration of between two curves. Alright, so for the next topic that we'll be teaching you is the areas between two curves. So earlier we discussed the areas under the curve, now is between two curves. So for the area between two curves, you can actually know that you have your two curves, because you have your y1 and y2. And for this example, this is your vertical strip. So for your vertical strip, you also have your y1, your straight line here, and your y2, or rather of the opposite. Your y2 would be your straight line, and this is your parabola, your y1. So some people said that this would be now your yl, your line of y, and your yp, your line of parabola. So when derivation of its formula here, if what you put or what you labeled outside, this would be now you minus by. So as example here, from this strip, I labeled this as your y1. I can actually also label this as y2, and that's up for me. So because the in integration in areas or application of integration, labeling is very important. So for me, that's actually I can label as anything as I would, as long as my teacher can understand. So this is my y1, the y parabola, or the outer, they would say the outer rather, or inner. I don't know, but my teacher that told me that would be, this is for me the yp, or the y parabola, and this is your yl. And this the same, the thickness is the same also, and from point here of the strip to the y axis, that would be your still your y. And if you put now, or you put it outside the strip, that would be the same. This is now the length here would be now your y1 minus y2, and the thickness of your strip is your dx. It's still the same actually, so or rather I would not encourage you to memorize your formulas, but rather understand it's because it's still the same. You just only have two lines. From the previous topics, we learned that under the curve is only have one line, so it's y. Now it has two lines, or rather two curves, so it's y1 and y2. You just minus them, and it will be still the same. So this would be now your differential area of y1 minus y2 dx. And if you integrate this, you integrate the differential area, that would be now y equals to y1 minus y2 with the limits from a to b dx. And this is for your vertical. And for your horizontal strip now, as you can see here, it's actually from the previous, it's still the same, but you need to label this correctly, because sometimes it's confusing. So as you can see here now, this is now your y, because it's what you call this, it's parallel to your y-axis, and you don't have your x, because your x will be all the variables here. So from this point here, I'll make it clear. So from here, this is your x1, the outer, and your inner here is your x2, and by deriving that formula, x1 minus x2, and this is your area of concern. And it's still the same, it has its what you call its limits, and be careful with its limits, because the limits in integration of area would be now what you call this is actually it's strict, because you need to derive something, because the area would be actually, what you call this, it's strict actually. So is this still the same? If you put out now your horizontal strip here, that would be now x1 minus x2, and that would be now its length here, and the dy is the thickness of your strip, and still the same, the differential area x1 minus x2 dy, and if you integrate that, that would be now area is equals to integral of y1 minus y2 dy from limits from a to b. So I think it's not actually, if you master or rather understand the under the curve, areas under the curve, I know between two curves will be now easy for you, because if you know how to label this and understand its formula, I know it's very easy for you. So let's go to your number one. or rather problem number one. The problem number one here. So actually, I know it's hard to plot, but I already do it for you. So it's still the same. When y is equals to x, and I put it here. So if y, or rather if x is equals to 0, your y is 0. If your x is equals to 1, it's y your 1. If y is 2, your x would be 2. And for here, and it's still the same, it's parabola. It's y squared. So if your x is 0, it will become 0. If your x is 1, it still become 1. And if your x will become 2, your y would become 4. So we'll just focus actually on the right side or the positive side. So now, if you plot this, that will become, put here 0, and it has the limits from 1 to 4. Or rather, you put your 1, 2, 3, 4. 1, 2, 3, and 4. So 0, 0, you put here. 1, 1, actually you put it here, 1 and 1. And 2 and 2, put it here now. And this is now your line. That would be now your line, and this is what you called your y1 is equals to x. You label this as y1 is equals to x. Now for your parabola, you now have this, and you have now 0, 0, 0. Your 1 and 1, you only have is 2 and 4. So if the x is 2 here, and the y is 4 here, so the strip would be, your dot would be there. So as you know, parabola, it's what happened here, it happens also in the other side. So that would be now, when you connect it from 0, 0, you connect it from 0 and 1 here, and now your strip would be from this point going to this point. Sorry if I'm not good in doing the plotting because I have a pen. If I have a pencil, it's easy for me actually. So now this is now how you plot this. I think I messed up here this part. So I'll get the white out. I'll do it again. So if it has its 2 and 2 here, this would be 2 and this would be your 2. When you connect that, you will do it this way, or now. And the parabola would be look like this. I'm doing it again, so I'll just cut the video, so I'll do it again here. I'll zoom in actually. Alright, so we're back. Please bear with me because I have a pen. It's hard actually to plot. So this would be now your x, and this is now your y. So this is your y1 equals to x, and your y2 here. Your y2 is equals to x squared. So this would be now your area of concern. And if we now plot the the horizon or the vertical line, a vertical strip rather. So this is your vertical strip here, and if this is your vertical strip, this from distance of y here on the x-axis to this point, this would be your y, or rather x, because it's aligned with the y x-axis, and it's still the thickness of that would be your dx, and this is your area of concern. And before that, notice here the point here from that point going to the x-axis here, that would be your y2, or rather your that would be your y2 or your y what you call this, your y2 or your y parabola. And from the top here, that would be now your y1, or that what you call your y line or yl, because it's a straight line, and this is the curve here going up, and that is your parabola, and that is your yp. And from this distance here, the in between of your y2 and your y1, that would be now your y1 minus y2. As earlier as I discussed, that is your formula. The in between here, from the distance from the top of the point of the stripe until the down or the bottom, that would be now your y2, and your formula would be y1 minus y2. So going back, if we put out now your strip, that would be now this. This is your vertical strip. I will label this as your vertical. Your vertical strip. I'll change my pen. So please wait a minute. So this is now your, or rather, I'll change it again. This is not my pen. This is it. So this is your horizontal strip here. Why is it my pen isn't working? I have actually many pens, but I don't know why it hasn't been working good. So just please bear with me by using this. Now this is your area or your strip, your horizontal strip, and this is your dx. That would be now the thickness. And from this point here, you bring out your y1 minus y2, because it's from the bottom here, rather from the top minus by the bottom, so that would be now the point from the top, or your y line, y line will be minus by the y2. So that would be now, if we use the formula, differential area is equals to y1 minus y2 times by dx. Then if you integrate this, that would be now your area integral of y1 minus y2 times dx, or rather dx, with the limits from a to b. So you might be wondering why ever since I haven't been talking about the limits. This is how you take the limits. It has its two intersection. That would be now your limits. But if you have a straight plane, or a what you call this, you don't have a proper what you call this, your Cartesian plane, you need to derive that. When taking the intersection or the limits, and you're taking the intersection or its limits, you just put y is equals to y here, the two y's here, and you substitute it to 0. So that would be now y, rather x is equals to y squared, and that would be now, if you transfer substitute it to 0, and that would be the x squared minus x, and if it's 0, you simplify it, you put out the x, and all you left is x minus 1. And as you can see here, this is now your x is equals to 0, and this would be now your x is equals to 1. So your limits is from x is equals to 0, and your limits from is equals to 1. 1 actually it has 2, rather 2 plus or minus 1. So that would be now your limits is from 0 here, 1 1, here 1 1, and 0. So that would be now a is equals to the integral of y1. What is your y1? Is your x. Minus your y2 would be x squared. And with limits from 0 to 1 dx. And you can just simply straight integrate that. That would be now x squared over 2 minus x cubed over 3 with limits from 0 to 1. So if you put, because this only cross out because this is 0, you multiply the number by 0, it's equals to 0, and this is would be 1. Any number raised, any exponent that has a number of 1, it's still 1. So that would be now 1 half minus 1/3, and your answer will be 1 half minus 1/3. That would be now 1/6 squared units. So this is now your final answer. If you're doubting your answer, just go here, integrate or input this in your calculator, and if you have the same answer, you have a correct answer. So, and for number 2, I will, for the number 2, I'll explain how the vertical and horizontal method will have the same answer, but it only has its different methods. Because if your vertical and horizontal method has still what you rather had have the same answer, meaning your answer is correct. So as per earlier, we'll just take out this area of concern. So that would be now your, if I have this, and this is now your line, and this is your parabola. Okay, and so if using a horizontal strip or horizontally, I'll put here horizontal with limits from 0, as earlier we actually answered it already. What's the limits of this? That would be 0 and 1 1 here. So if you have a, what you call this, if you can now plot this, actually the method is just different, but the answer will be the same. Oh, it has a bug. Alright, so you just need to manipulate the formula, or rather label it correctly. So as earlier, for this, because the strip is parallel with the x-axis, so we're going to use x. So this would be now your x. From this point here, your strip to the y-axis. That would be now your x. And from the point here, from the bottom point, that would be now, we can label that as this is what you call the parabola. So that would be now your x parabola. X, or rather x2, or x parabola. So earlier, the y is equals to x squared. We could manipulate that, so you crossed out, you substitute it to y, so, or rather, you need the answer 2x, so you take the square root of x, and y is equals to square root of x. So now your x2 would be square root of x, and your x1 is still x, or rather y, because x is equals to y and your y is equals to x. So this is your line. And now from this point here, again, bakit again, from this point here to the y-axis, so because we're gonna use y, because you only also use dy, and the thickness of the strip, that would be now dy. And from this is now your x2, because that is your y, or rather x parabola. And from this point here now, we're gonna use is your x1, and this is now your x1. So the area in between these two is what you call now your x1 minus x2, because this is the measurement of this strip, and you minus your x1, the first parabola, or rather the line, minus by the parabola. So if you take out now your strip, you put it here, that we could now label as x minus 1, x minus 2, or rather x sub 1 minus x2, and the thickness of this is your dy. And you can now shade the strip. Also here, don't forget to shade your area of concern. And this is for your number 2. So now, the differential area of x minus 1, or rather x sub 1 minus x sub 2 multiplied by now dx or dy. So now if you integrate this, that would be now x, or rather area, is equals to the integral of x minus 1, or I'm always what you call this, I always messed up, so that would be now x sub 1 minus x sub 2 dy, with the limits that we calculate earlier. The intersection is from 0 to 1. So if now a is equals to your x1 is your y, minus by the x2, that is the square root of y, the limits from 0 to 1. I'm so excited here. So that would be now dy. So if you now integrate that, that would be y squared over 2 minus 3 halves y over 3 halves of y, with limits from 1 to 0. So now, if a is equals to 1, as actually any number multiplied by 0, it's equals to 0. So that we cross out 0. So 1 is raised to 2, or rather squared, that's still 1. So it's 1/2. And now here is 1. The 1 is raised by 3 halves, so you put 1 raised to 3 halves over 3 halves. And your final answer, get your calculator. So 1/2 over 2, or 1/2 minus 1 raised to 3 halves over 3 halves. And your answer is 1/6. Your answer is correct, because earlier Because earlier, when we answered the strip, or rather the, what you call this, the vertical strip, the answer is 1/6. And now you're on the horizontal side, the answer is still is 1/6. Or rather, oh, I think I messed up. Oh, I missed the minus sign here. So I think I messed up. So again, let's do it again. Oh, I see it now. I missed the actually what you call this? I labeled it wrongly. So it was what you call this? Oh wait. Oh wait a minute. So this would be now your y1. Oh, I know now. I mislabeled it. So this is now your, actually that would be now your x2. Rather your x2 minus your x1, because in this is the outside part. So this would be now your x2 minus your x1. And because this is the outside part here, this would be now your, actually this is your wrong answer, but we're gonna fix it. So now, what you call this? So now this would be now, it should be, the answer is from, this is would be the square root. So the x2 minus x1, because the this is the outside part here. So this would be the x, rather I'm gonna do this again. I'm gonna cross this out. So that would be now a is equals to x2. Your x2 would be here, the outside part. The outside part here. Rather, this would be now, we label this as x2. And this is your x, or rather your x1. And this is your x2. Where's your x2? Yeah, so it would be x2 minus x1. So now that would be the integral of square root of y minus y dy from 0 to 1. So sorry, this is would be my mistake. This should be now, this is now should be this is the parabola earlier. So we should label this was the labeled what you call this, this is was mislabeled. So x2 minus x1, as I said earlier, could actually interchange your formulas. So now if you input this as your calculator, so, or rather we're gonna do it manually. So this would be now your 3/2 y. If we integrate this, 3/2 over 3/2 minus y squared over 2. The limits from 1 to 0. Actually, still this here. We just interchange it. So this would be now your what you call 1/3 1 raised to 3/2 over 3/2 minus by 1 raised to 2 over 2, and it would be still the same. And if you input that in your calculator, I'll be just redoing it again. I'll just erase this and rather minus by 1/2, and the answer is 1/6, not negative. So sometimes if you have a different answer, why not try to manipulate the formula, and if you get the correct answer, you're lucky. because you correct it. And this is your, don't forget to box your final answer. Oh, my pen is dying. As long as you understand you understand how it was derived, because this is the derivation and application of integration is very important. And also the labeling, because your labels will determine your formula. As earlier I mislabeled, so it, did you see how my final answer was different from this? So even though it's different, it's 1 raised to 3 halves over 3 halves, and this is 1, actually 1 half minus 1/3. So even though this is different method, or rather different strip, but the answer is still the same, so that is a correct answer. So that is for the area between two curves. So for the next video, or rather for the next topic, is polar coordinates. So let me take another piece of paper. Alright, for after the integration of area in between two curves, now we're in polar coordinates. So for polar coordinates, there's two systems that you need to be familiar with. The Cartesian plane, or the Cartesian coordinate system, and the polar plane system. First, in the Cartesian plane, you have this, as you can see, this is now, I think this is very basic for you, because this is came from the physics class, in which that r here, the radius, is equals to x is equals to r cosine theta, and the length here, or the height rather, is y is equals to r sine of theta. And actually, when you compute this now, you actually need the d, or by using d, that would be now your distance is equals to your what you call this, to your Pythagorean theorem. So in these formulas, you could now actually use a Pythagorean theorem. So in polar plane, so the polar plane here, you have it, you can see here, it has from 0 to 30, 60, 90, 120, so on and so forth. This is now your system, and also it has a radius of r is equals to 1, r is equals to 2, or so on and so forth. So when taking the concept of that is that, as you can see here, it's from the polar curve here. When you put down your strip, that would be the r and r, so is equals to r squared, and your thickness would be now d theta. Your thickness here is your d theta, and has limits from theta 1 to theta 2, or this would be now the final formula for this actually is this. Your area is equals to 1 half r squared d theta is equals to, from limits to rather, u1, or theta 1 to theta 2. And I want you to be familiar with this, that y is equals to r sine theta, and x is equals to r cosine theta. So this would be now the very basics, because this is, as you can see here, this is your y, the length, or rather the height, because it's parallel to the y axis, and still this is your x, and this is your point xy. So I think we're all set. So let's go now for the practice problem number 1. So for the practice problem number 1, find the area of the four-petaled clove, or find the area of the petal of four-petaled clover, in which x plus 2 plus y squared is equals to 100. Rather, I'm gonna do it again. So x squared plus 2 y squared is x squared plus y squared equals to 100. So this would be a circle. So as earlier, don't forget that I already said that your x is equals to r cosine of theta and your y is equals to r sine of theta. So if you substitute it now, that would be uh, x, or rather, let me, would be r cosine of theta squared plus r sine of theta squared is equals to 100. So if you simplify this, that would be now r squared cosine of r squared theta, rather cosine squared theta plus r squared sine squared of theta is equals to 100. So if you now see this, you could you could actually simplify this and make this as r squared is cosine of theta plus sine of theta squared. And take note that is cosine squared theta plus sine squared theta is actually equals to 1. That would be now, all you're left is r squared is equals to 100. So if you take its square root, so that would be now r, or the radius, is equals to 10. So this is example of the equation of the circle in polar form. Alright, so that's for number 1, the basic formula. And let's go, because as you can see now here, this is only the quarter angle, or quarter, you could say the 1/4 of the 4-petaled clover. So for number 2, this is the example. So I already and this is the example of the polar plane system. Find the area of r is equals to 5 sine of theta. So for you to get this, you first need that you input 0 to 360 degrees, that r, you need to substitute that r is equals to 5 sine theta. So now, if you take your calculator, go to mode 7, and that will appear as f of x. Then if you input 5 sine of x, alright, find sine of x and start from 0 and at least 360 degrees and put step by 30. So the answer will appear. So as you can see, don't forget actually then to go to change your mode to degree instead of radians, because if you take its integral, you go to degree, and if you take its integral, go to radians. If you now plot it in the Cartesian plane or the polar plane, that would be go to degrees. So let's copy it. So this would be now 0, 2.5, 4.3301, 5, 4.3301, 2.5, 0, negative 2.5, negative 4.33, negative 5, negative 4.33, negative 2.5, and 0. So, as you can see, that r is from the given here, r is equals to 5 sine of theta. As you can see, that 5 is its radius. That 5, it is radius. So, and you can put actually here that 1, 2, 3, 4, and 5. So you could now like to draw it a circle. You make actually like a system or a radar. Just please wait for a couple of minutes. So, as you can see now, it is 5 radius, and we could now input this we get from the tabular method of theta and r. So, you get now 0, 0 degrees here, 0, 0, go at 0. If you're at 30 degrees, you go for 2.5. So this would be 1, 2, and 3. So you're in between that, you're in between of 2 and 3. So for 60 degrees, it's 4.3301. So 1, 2, 3, 4. And then that's the in between in 4 and 5. So for 90 degrees, you go all out for 5. And for 120 degrees, go actually in 430 also. And in 150, you go back to 2.5. 1, 2, 3. So you're around here. And at 180, you go back at 0. So you could now see that, or just you can see that somehow it's like a perfect circle. You could portray that as your perfect circle. So this is now your polar plane. So actually now, even though if you input this here 210 degrees all the way to 360, it's still going to make this circle, because if you go, let's go. So this is from 210 degrees, it's negative 2.5. So if you're around here, that would be still it's positive. The positive that is in 210 degrees. So if you exceed here, this would be now a positive. Rather negative. This would be now in a negative. So it's still 210 degrees, but it's now in negative. So it is in negative 2.5. If you're around here, it's 0, 1, 2, and this is 2.5. It's the same that in 240 is actually a negative 4.33. So it's still the same. It's tag you or connects you to 60 degrees, that is in positive. And in 270, that's also in 90, and so on and so forth. So it creates a circle. Oops. It creates a circle that's as if it's your polar plane system. As for that now, if you can now, actually you can put now your strip here. If you put your strip here, if you put there your strip, you could now actually put the radius here, and this the thickness would be your d theta. That would be now your thickness, your d theta. So as earlier, as I said, that would be the what you call this, the formula. If you pull out the strip that you created, that would be now, this is your r and r. The thickness would be d theta. So if as you can see earlier, as I said, this is now your differential area. So differential area is equals to 1/2 of sine theta d theta. Actually, you can see it earlier, as I said, this. That is actually the Cartesian plane coordinates is from here. I'm teaching you how to do that if it's from the Cartesian plane to polar coordinates. From earlier, from the number 1, this is from the polar coordinates to Cartesian plane. So it's like it's exchanging its you can plot it in a Cartesian plane, or you can actually plot it as a polar coordinate. So as you can see here, that if in the concept of that is this r d theta is its thickness, and it has its two radius from left and right. Excuse me. So this would be now its sector, and this is actually now its basic formula. So now that would be, so differential area is equals to 1/2 theta squared d theta. That would be now, if you integrate this, it would be now a is equals to 1/2 theta squared d theta from limits. Actually, don't forget it has its own limits also. That it has its q1, as earlier, it's q1 or theta 1 and theta 2. So that theta 1 and theta 2 depends on what can you do from the 0, and anything you could choose from here, or rather from, actually you can only choose 2 that is in 90 degrees or in 180 degrees. It's from here 0 to 90 or 0 to 180. And I will teach you the two methods that has been taught to us. So if you now go with a 90 degrees, 90 degrees is equals to pi over 2. So now it has the limits from 0 to pi over 2, and then don't forget that 2 multiplied it by 2 if it's in the 90 degrees position. So area is equals to 2. You actually put 2 outside your 1/2 and 2, and that's equals to be 1, and this is pi over 2 limits. This is limits from 0 to pi over 2 theta squared d theta, and your theta here is the radius, that r is equals to 5 sine of theta. So that would be now a is equals to 4 wait a minute. So integral of 0 to pi over 2 for rather 5 sine of theta d theta squared. And don't forget this, you have to square it. So it's 5 squared sine theta squared d theta. So now if you input that in your calculator, rather this is not my calculator, that's my phone. Here's my calculator. So now if you plot them in the Cartesian plane, our polar coordinates, you go with degree. So now we're gonna integrate this. So first we go to 1, we go to mode, click 1, comp, then shift mode again. As you can see here, it has a 1, 2, 8, and 3 is in degrees. That if you're plotting this, you go for degrees. So we'll now integrate this. So go for 4 for radians. Go for 4, and the integral of, actually you could from this point here, you could integrate this now. So that would be 5 wait close open parenthesis 5 sine of x, 5 sine of x squared with limits from 0 to pi over 2. And so, the answer is 5/4 pi squared units. Actually, from this point here earlier, we could now integrate this. So, let's do it again. So, the integral of 2, you put 2 outside because that would be multiplied from 90 degrees. So, you put 2 outside. And then, if you're put 1/2, if you have a, a trash issues like me, so you can go back actually without from simplifying the 2 and you put 2 1/2 rather outside. We could do this even though you haven't simplified it yet. So we could now so we could now put here 5 sine of x squared, 5 sine of x squared dx, and with limits from 0 to pi over 2. Oh, wait, it's a syntax error. So let me, where's the syntax error? From 5 here. Oh, I see. There's a syntax error. So if we could take this parenthesis off. Oh, its answer isn't 25. I think we missed something here earlier. It is 25 over 4 pi. So let me do this again. If we put 1/2 outside? Actually, I see earlier. I only squared sine of x. And not 5. So if I do it again, let's say I put 1/2 outside, so it could be now simplified. It will be left is 2, rather it would be left is 1/5. So, also correct. I missed to put the squared at 20 or 5. I missed this to put the squared. So now this is your final answer. It's the area of 25 over 4 pi squared units. And so this is quite a fast and a lecture for polar coordinates, because we have so many more topics to be discussed, and we're gonna fit this all videos in 2 hours. So you still have now the area of application of integration in volume. So you have 3 methods there. So you have shell, you have disk, and you have washer. So this is for polar coordinates, and stay tuned to next part of the video. Alright, so we're finished with the application of integration in area. So now this would be now the part 2, or the application of integration in volume. So to be specific, this is the disk method. So in application of volume, there's our 3 methods. There's our shell, there's disk, and there's washer method. So for me now, we're gonna teach you on how to do the disk method. So for the disk method, actually, if for the disk method is only applicable for the vertical strip, and for the horizontal strip, that would be for the shell. But because of the volume, so it only has one for the strip, or one for use only. Not like in the other video on the areas, you could use it from vertical, or you could use it from horizontal method or horizontal strip. So let's get right to it. So as you can see here, I have a what you call this, a curve. I have a curve here that has limits from A to B, and as you can see here, in this method, you could only use a vertical strip, and as you can see here, my vertical strip is labeled as point xy, and with the width of, or rather a thickness of dx, and the illustration of the disk, and the disk is also in axis of rotation on the y-axis. So for the disk, the axis of rotation here is on the x-axis, and with the dx here, the what you call this, actually this is your y. If you have this your y, you have the from point here of the radius, actually the halfway of the what you call the disk, you have your y, your what you call this, your y, the length of your y. So now if you put that to what you call this, the if you want to derive that now, that would be now the differential volume of pi y squared dx. Then now if you integrate the differential volume, that would be now volume is equals to pi y squared dx with limits from a to b. So now this would be now the simple math, or simple what you call this, a simple illustration of the disk. So for the what you call now, for the question or problem number 1, as you can see here, I have now the x and y plane, and x and y is equals to x plus 1. So that would be now the problem is identify the volume if the area under the line of y is equals to x plus 1 with limits from x is equals to 0 to x is equals to 4 is rotated on the x-axis. So now it's rotated on the x-axis. So if you don't know how to plot the x plus 1, you could also use always the tabular method. So x plus 1, and if your x is equals to 0 here, you only have 1, so your y is 1. And you have 1, your y would be 2. Because if you have 1 here, 1 plus 1, that would be 2. So now you could now plot this. If you now your x is 0 and your y is 1, so this is your first point. Then if the x is 1 here and your y is 2 here, so this is your second point. Now this redirects you to your line, and always label your line, don't forget it. So this is now your y is equals to x plus 1 line. So the limits was given that limits from 0, x is equals to 0 to x is equals to 4. So we can label this as your 4, and this is now would be your limit. This is what's your limit. So this is your area of concern. So you could now put your vertical strip. So this is your vertical strip here. So the thickness of your vertical strip is still your dx. As I've what you call this? I repeated many times that if you're rotated on the x-axis, or you're doing it on the x-axis, you're gonna be using dx. If you're now doing it on the y-axis, and if you're in other words, if you're parallel on the y-axis, you're gonna use dx. If you're parallel with the x-axis, you're gonna use dy. So we're back it again, back where we started. So now this is your dy dx, your the thickness, and you could now shade your horizontal strip. So now from your point here, this is from your point here to y-axis, that what you call your y. And I think everything is set, so you could now plot your disk. This is now your disk. And this is your area of concern. If you put out your disk, or you illustrate it outside, that would be now look like will be this. Now, so this would be your now your thickness, your dx, and you have your axis of rotation on your x-axis. Now that would be now what you call this, your AOR, and from your point here, from the axis of rotation, that is will be your y, because it is on the parallel of the y-axis. Now that would be also parallel to your y, or that would be called your y line. From your point here to this, your dx, or the thickness here at the top, and in the middle your axis of rotation. So now if you what you call this, if you now set your formula, that would be now your differential volume is equals to, you have limits from 0 to 4, that would be now from limits of 0 to 4, and if you integrate your differential volume, and that would be now your pi y squared dx, that would be now your volume is equals to the integral of 0 from limit 0 to 4 pi, and your y is squared, that would be now x plus 1 squared dx. So now your v, if you expand this would be now, and you put your pi outside of the integral sign, that would be now v is equals to pi x squared plus 2x plus 1 dx, with limits from 0 to 4. And you can now actually integrate this, that would be now x raised to 3 over 3 plus x raised to 2 over 2. So you can also cross out the 2, when raised to 2 plus x, with limits from 0 to 4, and don't forget that it was multiplied to pi. So now v is equals to, actually now the 0 is not needed anymore, so that would be now 4 raised to 3 over 3 plus 4 squared plus 4. And if you take your calculator and put your calculator rather, so that would be now 4 cube multiply over 3 plus by 4 cube plus 4, and your answer will be 124 over 3 cubic cubic units. Yeah, your units that you'll be used in volume, remember that in volume you're gonna use cubic units, in area you use squared units. So to check if my answer is correct, you could actually always check in your calculator. So now go, as earlier, so I said, You go first to ship and mode. You go for number 4 for radians and go for the integral sign here. That has limits. So that would now you input that pi ship times 10 raised to x, close open parenthesis, x plus 1, so close, and raised it to 2 with limits from 0 to 4, and wait for the answer, and it's 124 over 3 pi. So you have your answer, and my answer is correct. I forgot actually the pi, and actually it's correct answer. So that's for number 1. And for number 2, actually you could actually take a screenshot of it, so you could actually take down notes, and you can now pause, and I could now get my paper for the next item. And for number 2, as I've searched earlier, that y actually now is equals to x, and with the axis of rotation in x-axis, and with the limits from x equals to 0 to x equals to 4. So how can you plot this if you only see this given? The only given is from x-axis and from limits 0 to 4 with y squared, y squared. So first you need to get you need to plot this. You input that in your tabular method. So if you put 1, square root of 1 will be 1. If you put 4 on your x, your y is equals to 2. So you could now have your 2 points here, and this would be, let's put it as 1 and 2, and let's put this in your x, that would be 1, and let's put this as your 4. This is your 0 and x axis, and this is your y axis, and it's rotated on the x axis. So we can now plot this as x is 1 and y is 1. The first point is here. The x is 4 and the y is 2. And you have your line as this. I always suck at using lines. So now this is your line, and it has limits from 0 to 4. So as you can see now, you could actually input anywhere your vertical strip, so, and you just label everything. So from this point here, you could now input your line, that is your y, because the length of the horizontal strip is parallel, your vertical strip is parallel in the y-axis, so this would be your y, and your thickness would be your dx, and in this x is parallel from this point, so this is the measurement of your x. So now, and you can now shade your area of concern, and shade also your strip. So now you could now plot your disk. This is the shape or the face of your disk with the axis of rotation at x-axis. So now if you put out your disk, this would be the looks of it, and this has your thickness, that would be your dx, and this is your area of axis of rotation rather. So this is from the axis of rotation, your radius here, your radius from the top and that would be now your measurement of your y. And actually everything is set, so you could now derive your formula. So it's still the same, that the differential volume is equals to pi y squared dx. So if you integrate now your formula, that would be now your volume is equals to pi. You have limits from 0 to 4 pi, and your x, or rather your y, is x square root of x squared dx. So actually you could cross out the squared and your square root. That would be now the integral of pi x dx with limits from 0 to 4. So you could now actually integrate this, and that would be pi x squared over 2 with limits from 4 to 0. And now, if you substitute your x to 4, and actually this 0, you can cross it out. That would be now pi 4 raised to 2 over 2, and that would be 4 raised to 2 over 2, it's 8. So your answer is 8 pi cubic units. Now if you check it by using your calculator, as earlier as I said, so you could now input this in your calculator. So that would be pi, shift pi and alpha x from limits of 0 to 4, and that would be 8 pi. So my answer is correct. And this is for the disk method. So thank you for watching, and next will be your shell method. Oh, I think it has marks, so I'm gonna change my paper again. Alright, so we're now on the second topic at the application of integration in volume. So this is now the shell method. So for the shell method, actually it's closely the same. So it's the same method. Rather, you can have the same answer from the first method, that is this, but you can only it depends on how you manipulate its formula. So as you can see here, that this, you have a line and with the limits from A to B, and it's still the same, that you plotted your rectangle or your vertical strip, and which what you call this, parallel with the y, and from the distance from the origin, from the rectangle, is your x, and still its thickness is dx. So now you can plot your shell. When you plot your shell, you make sure that how much is the area in here, you put it also here, because that is its center and its radius, So if you now put your shell here, or you put it outside, it will become a cylindrical tin can, so such as it looks like a Coke in can, Rolla in can. You could see it as like that. So that has its area, axis of rotation in the y-axis. So, and the x is always also it's the radius, and the length here, the height rather, so that would be y, and its thickness is dx. So now if you manipulate this, so you cut it in half like that, so like it will spread at, it will make a a rectangular shape, and that would be now turned to 2 pi x, and still it has its thickness, that is your dx, and the length of that would be now your y, and this is your differential volume. This because it's an example for the area of what you call this, the of a square, what you call the volume of a square. So this is that example. Rather, the formula for that would be length times width times height. So what you call the let me draw a circle here. That's like that. So it's length times width times height. It's the same as this also. It has its length, its width, and its height. So now that would be your, and this is also your differential volume. It's inside. So differential volume is equals to 2 pi x times y dx. So now if you integrate this, the integral of differential volume is equals the integral of 2 pi xy dx. And with the limits from a to b, that would be now the volume is equals to 2 pi xy dx. And this is now your formula. So, for question number 1, the curve y is equals to square root of x, and the region bounded by y is equals to 0 and x is equals to 4, and is rotated about the y-axis. So this is your y-axis, and this is your x-axis. So now this is 0. If you don't know how to plot, still you're gonna use its tabular method. So you're gonna use tabular method here, or rather I copied the wrong what you call this, the wrong the wrong given. So this is not actually square root of x. This should be now the 2x squared. So this should be the 2x squared, and if this x squared here, this is now, as you can see, this is a parabola. So if you see that a parabola, you can plot easily parabolas. So if you put 1 here, if you put x as your 1, that would be now also for 1. If you put 2 as your x, that would be now 8. So you now have your 2 points. So we'll only focus on the one side of the parabola. So now if you put here 1 and 1, this is your first point. And now if x is 2, let's say in here the 8, this would be your 8. So this is your second point. So now when you graph the parabola, so it looks like this. But we're gonna focus on its left side. Oh, I think I messed up again. Alright, so and now it has limits on y is equals to 0 and x is equals to 4. Let's say I'll put this as your 4. So we could close the limit. Now, so this is now your area of concern. So actually now you could actually plot your vertical strip here. Let's say this is your vertical strip with the length of your x here, which is parallel to y, and also you could put your x here, that is parallel the distance from the origin here to the horizontal vertical strip. So, and the thickness of that would be your dx. So now we could shade your area of concern. And now, for the shell method, we could now actually plot your shell, your cylindrical tin can. Now, if you put the cylindrical tin can outside, so this would be look like this. That has its area of rotation, axis of rotation rather. So that would be now axis of rotation on y-axis. Then from distance from the radius here to this point, that would be now your x, and from this point here, its length, that would be now your y, and it has its width, or rather its thickness, be dx. So if you open further and manipulate its formula, we could now, because of the what you call this, it's the axis of rotation. So now you could open that as this. So you cut it in half, and it would like form a rectangular shape. So now it's still the same actually. So if you have this would be now your the dx, the thickness, and this is the length, it's y, and now this would be now be different because it will be now cut it in half, its radius. So the radius would be now 2 pi of x. Instead of r, that would be now your x. So the formula would be now the differential volume of 2 pi x y dx. That would be now volume of 2 pi x, which your y is 2 square root of 2 dx, with limits that was given to you is 0 to 4. Now, if you now integrate this, you put 2 pi outside, 0 to 4, and the integral of this, would be now 2 x raised to 3, or rather what you call this now, 2 raised to 3 over 3 here, and now your answer, or rather the limits, from 0 to 4. And now v is equals to 2 pi is still the same, that x is equal, number will be multiplied by 0, the answer will still 0. So 2 times by 4 raised to 3 over 3, that would be, get your calculators, that would be 2 pi multiplied by 2 times 4 raised to 3 over 3 equals to 256 over 3 pi cube units. If you now want to check if your answer is correct, you could actually do that. So this would be now 2 pi multiplied, close open parenthesis, 2 x raised to 2, close the parenthesis, with limits from 0 to 4. So the answer is 256 over 3 pi, and this is your final answer. And that's it for number 1. For number 2, let me get a new paper. For number 2, For number 2, the curve y raised to x 1/2 and the region bounded by y is equals to 0 and x is equals to 7 and rotated about the y-axis. The curve y x raised to 1/2 and the region bounded by y is equals to 0 to x and x to 7 and rotated about the y-axis. So if you now plot this, y x squared, or rather y raised to 1/2, if you plot that, would be x, still using the tabular method, that would be, if x is 1, x raised to 1/2, still your 1. And if x is 4, that would be x 2. Let me check. If 2 raised to 1/2, rather 4, not 2. Oh, so it's 2. So this is correct. So we can now plot the curve. So if x and y is 1, so put here 1 and 1. And if x is 4, let's say we put 4 here. So we put there 4. When you put 4 there, actually let's add also the I think it's not enough, or the limits that is equals to 7. I think we need to add if the x would be 9, the y would be 3. Let me check. So correct, the y would be 3. So let's say this would be your 9 and this is your 7. So now if x is 4, your y is 2, let's say this is your 2. So your curve, or the next point, would be here. And then if its x is 9 and y is 3, and y is 3, this would be here. And your line will connect. But yet, your limits is only until from 7 and 0 to 7 rather. So, you can now actually plot your strip. You can now plot your strip here with this, your length that is parallel to y is y, or y-axis rather. And from this point here, you could now plot your x, and with the shaded region. And still the thickness would be your dx. So now I'll just speed the process. This would be now a shell, or rather a tin can. So now if you place this tin can outside, this would be looks like this, in which it has a axis of rotation at the y-axis. So it has from this point the radius, if from that distance, this is your x, and from the length, or your length rather, this is your y. and it has the width of dx. So if you cut that in half, still that would be the radius of this, because if you cut it in half, it stays like that to make a rectangular shape. The radius would be now the 2 pi of x, and still its length would be y, and it has the thickness of dx, and that is your differential volume, or rather inside is the differential volume. So the differential volume is equals to 2 pi x, 2 pi x multiplied by y dx. Now if you now integrate that, that would be now the volume is equals to the integral of 2 pi x multiplied by y dx with a limit from 0 to 7 as for the given. Now if volume, we would put outside the 2 pi, then rather not the integral, so that would be now x multiplied by x raised to 1/2 dx, or rather let me do it again. So this would be your integral sign, which has a limit from 0 to 7. So this would now the integral of 2 pi, or rather 2 pi, the integral of x multiplied by x raised to 1/2 with the limits from 0 to 7. Now if you add or you distribute x raised that inside of x raised to 1/2, that would be 7 pi of x raised to 3/2. That still is, that's because 1 plus 1/2 is equals to 3/2 dx. And now if you integrate that, that would be 2 pi equals to x raised to 5/2 over 5/2 with limits from 0 to 7, and still 0 is 0. That would be 2 pi of limits from 7 raised to 5/2 over 5/2, and get your calculator and compute that. 2 pi times by 7 raised to 5/2 over 5/2. And the answer is 325.8254. 325.8254 cube units. And we could use this formula here. We could use that to input it in the integral, input that into the calculator, and for use it to check if it's correct. So that would be x alpha x raised to 3/2 dx with limits from 0 to 7. Or rather, wait, I missed something. So let's gonna do it again. I missed the what you call this, the 2 pi. I missed 2 pi, so 2, you put 2 pi outside of the integral, and let's do it again. Wait, just wait a minute for a couple of, oh, it's correct. So it's 325.8254 cube units. And so this is for your number 2, and using shell method in application of integration in volume. So this is for shell method, and wait for the next video, or rather for the next topic, that is washer method. So let me again find me a clean sheet of paper. Alright, so we're reaching our last topic for the lesson in application of integration in volume. So This is now the last would be the washer method. So as for the washer method, we have here the curve AB. This is would be now its area of concern. So the curve AB, and now if you put here, I put here a point in which I could create a strip, because you put the strip here anywhere and then name the strip at strip XY. You could actually now create a washer. A washer has a big circle, and also a washer that it has its hole in between. So you need to compute its circumference, or rather the hole of the washer, and in the whole circle of the outside of the washer. So, and washer method is always perpendicular to its strip. So like, if it is strip here, if the strip is what you call this, if the strip is on or vertical, its axis of rotation would be perpendicular, and this would be now on parallel to the x-axis. And actually, the washer method, you can actually interchange that, whether you want it to be uh, what you call this, horizontally or vertically. So that the way you will compute or solve the problem in washer method. So for corrections first, actually, what you call this, I thought, my lessons, on my past lessons, actually, if what is was given, actually, I mean, rather, the if the strip is only for the vertical, it's only for the vertical, like in volume. So if it's vertical, it's only vertical method, cannot be used by horizontal strip. So that's example for uh, the what you call this, the shell method, and the shell method and the disc method. So alright, so if you now see here, if you zoom in here, this part, the what you call this, the the washer method has actually another way of, like, the axis of rotation has is also its coordinates. So that would be now y is equals also to b, because sometimes you can only put here, or you can actually assign a coordinate that's for axis of rotation. So for the formula here, you could now see it here. The axis of rotation in between passes through the hole of the washer. From that hole, in the middle, from the hole of the washer to the top, that would be now its b of your length, or rather your length. Rather, that would not be a b, that would be a y, not b. And so, rather, that this would be now your b. And in between here, from the axis of rotation and the circumference, or rather the radius of the hole, that would be now b minus y, because that's what is in between b, and y has its own coordinates also. And still, the dx, it has its thickness. So now if you derive that, rather if you solve that, that would be now the differential value is equals to the integral of pi b squared dx minus pi multiplied by b minus y dx. So now if you integrate this differential volume, you can now get that. And also, you could, if you simplify this, you put pi outside also in dx. So you can simplify that as pi multiplied by b squared minus b minus y dx. And this is for its formula. Alright, so for number 1, we have here the given. We have the given is on if the line is x cubed, the line will be straight. And now if we have the parabola here, the line would be rather the what you call this, the curve passes going up. So this is the what you call this, this is the given. So first we need to find its intersection here, this intersection, because this would be now what you call this would be now represents our limits. And to get that is you can equate your x, your y square, y sub 2 and y sub 1, you put it here, your x is equals to x cubed, and you substitute you solve it to 0, so that would be now 0 is equals to x cubed minus x, and that would be 0 is equals to x squared minus 1. We put we simplify that and we put x outside, and that would be now x here, that would be equals to 0, and this would be x is equals to 1. So you have now your intersections, so this, or your limits, so rather 0 and 1 1. And actually you could now put your strip. So as for the example here, put your strip. Now you could put your point here, and from the distance of that, you could be now from the distance of the point to the y-axis, that still would be your x. And don't forget to label your lines. This is for the parabola or the curve, that would be for x, and for the straight line, that would be for x cubed. And now here, this also applies from previous methods, or previous previous formulas, that if what is in the top side here, or the inner for me, this would be my inner line. This would be now my y1, or rather y2, not what you call this, that would be now rather this. Oops, I made a actually wrong decision. So this would be your x. Wait, this is for your, let me do it again. That's why I think it's something wrong, because I know that parabola here is not x. So that's now your y1 is equals to x cubed, and your y2, that would be now your x, because that is a straight line. So I need to change it first. Also, sorry for my mislabeling. So your y squared here, your rather y sub 2, your x, be now on the outer side, that would be now, would be now your y1, and this your inner or outer, the parabola, that would be now your y cube, and that is your outer rather, and that is your y2. So, and in between this is still your dx, the width, and you can now actually plot your washer. In which it has its axis of rotation in the x-axis. So if you put this out, or rather what you call this, you pop it out, so this would be now So this is the axis of rotation, and AOR. Alright, so from this distance, your axis of rotation here, and from the radius of the hole, that would be now your B, or if that's your B, that would be now your Y1, because yeah, it's what you call this, that is would be now your that's connect that it is connected to your Y2, or rather Y2, not your Y1. So this is your Y1, the YL, or that is Y of line, and this is now your Y of P, or Y of parabola. So now we could go to derivation of its formula. That would be now, or rather V, not A. So the differential volume is equals to the pi of what you call this, pi of pi of yx, or rather pi of y1 here, squared dx, minus by pi of y sub 2 squared dx. So now if you integrate this to get the volume, or rather the volume, that would be now pi, integral of pi of y1. Your y1 is your x, dx squared dx, minus by the pi of what you call this, y3, y sub 2, and that is x cubed squared dx. Now if you simplify this, you could now put the integral of pi outside, x squared minus by x raised to 6 dx. So this is now, so actually now you could input this in your calculator, or rather you could also do it manually. So if you're doing it manually, so that would be now V is equals to not V, so that would be close open parenthesis pi x cubed over 3 minus x raised to 6 over 6, rather 7, not 6, raised to 7 over 7 with limits from 1 to 0. So earlier, as I've said, I computed its limits in 0 to 1. So that would be now its limits. And actually, if you this pi goes to 1/3 over 1, and 1 raised to 7 over 7, still the answer would be pi multiplied by 1/3 minus by 1/7. And the answer is, if you compute that, so get your calculators, so 1 over 3 minus 1 over 3 minus 1 over 7, that would be now 4 halves 4 over 21 pi. Now if you input that in your still calculator, you could now get the answer. So this is now your final answer for number 1. Alright, so for the next would be for number 2. For number 2, we could actually now try it's what you call this, it's horizontal method. So for the horizontal method, the given are what you call this, you only have a given are, it would be still the same. that alright, so this is now for number 2. Get a new piece of paper. So for number 2, it's still the same. The given would be it has a line of with the line of this and a curve. So it has a line of x squared here is equals to y, and rather x sub 1 x sub 2 would be y, and the y sub 1 would be square root of y. Actually, this is 2, not 1, because it's a parabola. So as I've been computing it in this form. Actually, I've been computing its what you call this, its intersection, and that would be still 1 and 1, or 0 and 1. And I think everything is set, because, and also the axis of rotation is in your y-axis. So the axis of rotation in washer method, that is the perpendicular to its what you call this, to the strip. So now the strip we will be using, it's a horizontal strip. That's what I've been saying, that in washer method you could interchange whether you want it to be on the horizontal or the vertical or the horizontal strip, because you could also use the same method. And for now, this point here could be now your x sub 1, rather your, this is your x sub 1 here. So from this point here, this is your x sub 1. From this point also, from the outer, or rather this is the outer circle or outer line for your that, because it's in the x-axis, this is your outer, and this is your inner. So this would be now, this point here is your x sub 2, or that is the parabola, and still this is the thickness, and that is your dy, and shade the area of concern, and you can now plot your washer. As your for washer, you could now have this. So if you pop this out, this would be now look as like this, and it has a hole, and this looks now like a washer. It has a hole in it. So the axis of rotation is here, is in your y-axis, and from this point here, this is your x sub 2, and from this point here, this is your x sub 1, and the thickness here is your dy. So to put that into context, that would be now dv, or you put that in the formula, that would be now dv is equals to the pi of x sub 2 squared dy minus pi of x sub 1 squared dy. So if you integrate that, so that would be now the volume of the pi with limits from 0 to 1. And if you simplify this also, you put pi outside in the dy, that would be now equals to x sub 2 squared minus x sub 1 squared dy multiply. So if you now substitute 0 and 1 pi, your x sub 2 now is y squared, or y squared and is raised also to 2, that would be now 4 minus, and your y here is y square root of y here, square root of y. If you raise that to 2, you could now actually cancel out this. So would be now the pi 1 0 y raised to 4 y dy. So you could now actually integrate this. So this would be v is equals to pi of y raised to 5 over 5 minus y raised to 2 over 2 with limits from 1 to 0. So v is equals now to 1/5, because 1 raised to 1, raised to 5 is still 1, and 1 is raised to 2 is still 2, rather still 1, that v squared is equals to, if you get now your calculators, that would be now 1/5 minus 1/2. The answer is, what you call this, the answer would be negative 310 pi. If you now check cubic units. And this is now your final answer. And for today's lecture video, this would be now my last, and this because this is the shell method, and this is the last topic in integration, application of integration in volume. So please like, comment, share, and subscribe to my YouTube channel, and please please learn from my master video number 2. Peace.